Welcome to my talk for the CVPR workshop on event-based vision. Let me share my screen so we can start. And then I'll start the presentation. Okay, so the title of my talk is let me move this out of the way here. Okay, should be able to get it this time. Okay, here we go again. Okay, this is better. Okay, so the title of the talk is Routing Events in Two-Dimensional Arrays with a Tree. This is work done with my former student, Sam Folk, who is now CEO of Femtosense Inc. And I am Kwabena Boahen from Stanford University. So the problem we are interested in is as follows. We have a 2D array of pixels here, and we would like to be able to communicate information to and from the environment from this 2D array. And the information is the form of spikes or events, as they are called. And to send these events to the environment, we use a transmitter interface, and to receive events or spikes from the environment, we use a receiver interface. So it works like that. And I'm going to be using the word pixel and neuron interchangeably, but so just bear with me on that. And I know you guys are mainly interested in images and pixels in this audience. So basically the goal here is to be able to transmit and receive up to 1,000 events per second per pixel. And the assumption is that the pixels are sparsely active. And so you can exploit this to minimize latency and maximize throughput. The way that has been done in the past is to use a kind of row column organization, which is just like what you see in a normal kind of imager that just is frame-based, where you have row and column select lines. And in our case, we also have these addresses that identify which pixel is to send or to receive an event. And we call the column address the X address, because this is the X dimension, and the row address the Y address, because that's the Y dimension. And the nice thing about this approach is you basically only need about square root n circuitry to service n clients, which are pixels or neurons. And what is not so good about it is that you end up, have all kinds of race conditions, because you're sharing these column and row lines among all these pixels. And you have to make some timing assumptions. And as the array gets bigger, these problems get exacerbated. And also the throughput goes down. And so the original proposal, which goes back to the early 90s from Kavamid's lab, was to basically use these arbitraries to select which pixel gets to send its event. And the pixels initiate the whole thing by making a request to these arbiter cells, which then are going to arbitrate and select a particular row, right? And these requests from the pixels go through a wide or are collected by a wide or. And once a particular row is selected, an encoder outputs the row address. And then the pixels also in the selected row then get to drive these column lines to drive their data out of the column lines. And for each of these activated columns, you're going to use another encoder to generate a column address. And so that's the basic idea. And so let's talk about the various blocks one by one and what are the challenges you face in designing this system. And so just to make it more concrete, let's just look at the circuitry in the pixel. So the idea here is that, that's what it looks like. This is the interface between the neuron or the event generator inside the pixel and the row lines, request and acknowledge or select, and the column data line. And basically, so PI is the pixel request, active low, W is the row request, S is the row select, P0 is the pixel reset, and CO is the column output data. So now let's talk about, the next step here is the wide OR. So this connects many pixels to one, input of that arbitrary. And in order to actually do this safely, when the row gets selected, additional pixels are prevented from generating new events. That way, the pending events could be cleared and we can detect that, and then we can withdraw the select. And so basically, what's going to happen is when we are selecting the array, we may end up with a race between some pixel that's just trying to make a request while we are selecting. And so you have to watch out for that. And similarly, there's an issue with the wide OR that runs along that sends the pixels data along the column line. And in that, multiple columns can be active at the same time. And we're going to latch these signals. And if a signal is too slow, it's not going to register. So we have to assume that there's a minimum difference in delays to these column signals. And now let's talk about the arbiter. The arbiter also presents various challenges, and one of them is trying to be efficient in terms of the order in which you select these rows or columns, and at the same time be fair, not resend a particular row or column while other requests are pending that came in earlier. And so the fair greedy arbiter, which is shown here, going back to work we did in 2004, solves this problem by doing a servicing request breadth first. Basically, it does a breadth first search of the tree for new requests. This means that if it's down a certain leaf and the next leaf nearby makes a request, it's just going to service that next instead of going back all the way up the tree and coming back down. But in order to prevent this particular, local part of the tree from constantly being serviced, we're going to latch the requests that are pending when we select a particular subtree and send those and then clear the request, or wait for the request to clear and then clear the grant. And this will prevent the child from requesting until we've serviced the whole rest of the tree. But then again, while we are sort of latching those pending requests, if a request just comes in at that time, we're going to have a race condition again here, which we need to deal with. And so basically, that's the last critical component here is the column encoder. And this is in the critical path. It determines how fast we can cycle and read out events. Basically, because this address encoding of each column has to happen sequentially. And, as we get more columns, we have to drive more capacitance. And so it takes more time. And so as the arrays get larger, our throughput is going to be dropped. So that's limited the performance of this architecture, to less than 50 million events per second. And so how do we get, beyond that? What people who are pushing the envelope in industry have done, and here's an example of state-of-the-art from Prophecy, is a 1280 by 720 pixel, that's HD array, event-based vision sensor. And it actually consists of two chips. You're seeing the chip on the top side, which is the pixel array. And then the chip on the bottom side has all this digital circuitry to do the readout and so forth. And so basically what you have with the top chip is fabricated in 90 nanometer backside illuminated CMOS image sensor technology from Sony. And the other chip is fabricated in 40 nanometer CMOS. And these wafers are bonded together such that each pixel can send its signal to the chip underneath. And they've showed some nice demos here of doing like 3D stereo with strobe light. And they can achieve up to 1 giga events per second. So this is like 20 times higher throughput than we are used to. And the way they do this is basically, let's describe what's in the pixel. This is kind of your standard approach for contrast change detection, where you take your photocurrent and you logarithmically convert it into a voltage. And then that voltage goes into that sort of basically, and this part here, light sensor is on the top die. And then the bottom die has this change detection, which uses adaptive delta modulation. Basically, it's looking for if contrast changes by a setting amount, then that corresponds to an equal amount of voltage. And so if the voltage changes by that amount, then you trigger an on event if it's an increase in voltage, or off event if it's a decrease in voltage. And so that's basically what's going on inside here. And if you now look at the architecture that they are using here, you can see it's very similar to what I just described with the what's called the burst mode arbitered design, row parallel readout. So the pixel, when an event is generated, you get this row request. The row then it gets, the arbiter then selects a particular row, generates that row address. And then the pixels in that row get to, in parallel, send out their data, basically activating this line or that line, or both, depending on if they have an on, off, or off event. And so basically, since you've got 1280 pixels, you end up with 2,560 signals, bits of data, basically, and a 9-bit address. And so again, instead of then going and encoding these column addresses one by one, which would slow you down, they've introduced something they call the event signal processor. And this replaces the column encoder. And what they do is they immediately timestamp the raw data they just read out with 1 microsecond resolution. So this preserves the time and precision, even though there may be some buffering and some delays, and even if the recipient is not responding. And they've managed to be able to, by looking at the spatial and temporal redundancies in these pattern of bits across the entire row, they are able to compress the number of bits they have to send down to 1.6 bits per event when at high loads, when you really need to get the bandwidth. And so with that compression, if you have a 100 megahertz interface here with 16 bits in parallel, that's allowing you to get to 1 giga event per second. And so this is really fantastic design. And but how far can we take this? Okay, and let me just show you some pictures first before we talk about scaling. And so here is data from the camera provided by Chris Posh. And you can see here it's a street scene in Paris, I presume. And you can see everything that's gray are pixels that are not active. And when you get an on event, you light up that pixel in white. And when you get an off event, you light up that pixel in black. And what looks training the cars back here are the shadows from the sun, but you don't quite see them because that's your nice dynamic range you get from, you can actually see equally in the shadow as you can in the sunlight. That's the contrast sensitivity and the high dynamic range. And you can also see how sparse the activity is. So these are all advantages that people are excited about exploiting in automotive or industrial robotics applications and so forth. Now, let's then, okay, I think I need to get it to go to the next slide. Okay, so the main limitation we face here as we try to scale to bigger and bigger cycles are these wide ORs, sizes, these wide ORs. Because what you've got here is basically, as the row and the column lines get longer, the capacitance distributor along the total capacitance and distributor across these lines increases. This voltages takes longer to equilibrate across the whole line, the whole wire. And this degrades your signal integrity as well as slows you down. And so what we are proposing here is that now that we have the ability to stack two chips, we no longer have to constrain the interface circuitry to the periphery. We can actually move it underneath the array, okay? And so this opens up new possibilities here, which I'll show you basically address a lot of the issues we're running into. So in particular, we're proposing that we use a tree-like router. And the idea here is that each parent here, depending on whether it gets a request from this daughter or that daughter, before it sends the data from the daughter, it sends a bit indicating where it came from. And so you can see we generate one bit of the X address this way, or column address. And then when we go in this direction, between these two sides, we generate one bit of the Y address. And as we go up the tree, we generate more and more bits, which could be either, prepended to the bits from the lower level to generate and communicate it serially, or it could be, you could add more wires so you can send all these bits in parallel. And so let's talk about the pros and cons here. So we got rid of these wide ORs. That means that we get rid of the race in the row of pixels. We don't need to worry about these match delays in the columns. And we have a much more scalable design. And, we also get rid of the row, the column encoder bottleneck. We remove it from the critical path because we are encoding the address even while we are arbitrating. Those are happening concurrently. And, so encoder is no longer in the critical path. And that also, not having to go up the tree and then back down, gets rid of this sort of child request parent grant race condition. And so those are all great. What's not so great is that there's other end costs now. The amount of circuitry we are using to do this is, scales as the number of pixels, not like the square root. And so, we go in with a serial approach where you send these bits over the same set of wires helps to reduce the cost of this, but albeit that's at the expense of more transistors, as you would see. And so let's talk about this bit serial communication. So the pro there is that it accumulates an arbitrarily large address space. Because no additional wires are needed, you just append more and more bits as the address space increases, and the levels of the tree increase accordingly. And then the pro, again, is that it accommodates data as well. We can just append even additionally more bits as data, right? And then the con here is there's less throughput, than going parallel. So by saving wiring, we basically reduce bandwidth, but you can not do that if you need more bandwidth. And so we actually implemented this tree router, both for receiving and transmitting, in this test chip called Braindrop, which was fabricated in 28 nanometer 1-poly 8-metal FD-SOI process. And it's got 4,096 spiking somas, 1,024 synaptic filters, total of 64 kilobytes of weight memory and 100 kilobytes additional memory for buffering events and addressing and routing them and so forth. And the main array of neurons and synapses consists of a 16 by 16 array of these tiles here. And each of these tiles has 16 spiking somas and 4 synaptic filters. And so this means that we've got to sort of build a tree that can accommodate that many leaves, that has that many leaves. And so if I put back the metallization layers, here you can start to see an idea that there's something like a tree in there. And if I take away everything by those two levels of metal we're using throughout the tree, you can see that we actually have two H trees in here. And then these regions in which the circuitry that's in the nodes is residing in. And so one of those trees is for the transmission of events. So it's got 4,096 leaves, which means that we need 6 levels. The first 2 levels are inside the array itself, the tile itself, because that takes us from 1 to 4, the first level, 4 to 16, the second level. And then levels 3 through 6 are shown here in these color codes. And we also put in these repeaters, which are just buffers. They don't latch the data, they just restore the signal, so that we don't to maintain the speed here. And then running in parallel with that, we have another tree that is going the other direction. Events or packets are coming in, and they are being routed down to those 1,024 synaptic filters. And so in this case, we need 5 levels, right? 2 to the 5, or 4 to the 5. And 1 level is inside the tile itself because there's 4 synaptic circuits. And then levels 2 through 5 are shown here in these color codes. And then again, we have repeaters driving the other direction. And so if we actually show you more detail here, like this, going back and looking at the tile, you can see these are your analog neurons and synapses, somas and synapses are here. There's actually a config SRAM that can configure the properties of these neurons and synapses. And so the receiver actually can deliver payload that's used to program this SRAM and change the config, as well as delivering these spikes to the synapses. And then here you can see the circuitry that implements levels 1 and 2 of the transmitter, as well as level 1 of the receiver. And then this cutout here is used for all the circuitry in the higher level nodes, like you saw in the previous slide. The whole array of this is about 30 microns this way by 40 microns. And what we're actually using is a 4-array tree, not a binary tree like I described it. And that's why we have 6 and 5 levels, respectively. And so basically each node in the transmitter tree has 4 daughters, and each node in the receiver tree has 4 daughters as well. And the way we communicate along these links or these channels is using a serial link, serially, and there's actually 6 signals, and I'll describe how they operate in the next slide. And you can see here, this is the stuff where there's the transmitter level 1 and 2 and receiver, and the cutout is the upper levels of the tree, as I mentioned. And so why a 4-array tree? Well, we basically found that actually uses fewer transistors than a binary tree. And also, since there are fewer levels, it's also going to take less latency to get up there. So let's look at it. So here I have 2 trees. I have a binary tree with 4 leaves, and I have a 4-array tree with 4 leaves as well, okay? And in general, if I have a tree with n leaves, then in the binary case, I need n-1 nodes, which is 3 in this case. And in the 4-array case, I need n-1 divided by 3, which is 1 in this case, right? So you can see that even though we have the same number of leaves, the 2-array tree or binary tree is using 3 times as many nodes. Okay, so if I can build these 4-array nodes here with less than 3 times as many transistors, I'm going to win. Okay, so how does that work out? Well, it depends on whether you look at combinational circuitry or state holding circuitry, like this NAND gate here or like the C element. Okay. And so this is the case for the binary tree. These 2 input versions of these gates use that many transistors. And the 4 input versions of these gates use twice as many for the combinational gates, the 4 input NAND, and 1.5 times as many for the state holding gates, the 4-input C element. Okay, so you can see in the worst case is that I double the number of transistors, and that happens for the combinational circuits. And so I basically, yeah, so I'm basically potentially, reducing my total amount by 32% or so. Okay, sorry, it's 1/3 the node. So anyway, we'll work it out here. And so actually, we made the design and we counted all the transistors, and we've saved 13% to 45%. Okay, so if you look at the transmitter, the leaf nodes have this many transistors, and the intermediate nodes have that many. And then across the total tree, we are using like 13% less transistors for the 4RE tree. And for the receiver, leaf nodes have that many transistors, and intermediate nodes have that many transistors. And in this case, overall, we are using like something like 45% less transistors. The reason we don't save as much in the transmitter is that we actually end up having to, implement the arbiter with a 2RE tree, right? Because there's no such thing as a 4-input arbiter cell. The way you build a 4-input arbiter is you take one of these mutual exclusive elements and use it to decide which one of 2 inputs you're going to pick. And then you tree 2 of these ARP2 circuits and decide between them with another mutual exclusion unit and end up with a 4-input arbiter that looks like that. And so that's basically how the numbers come out. And as to the protocol for communicating over these serial links, here's how that works. I'm going to talk about just a 2-input, signal version. So this would be a case where we're just sending 1 bit. If the bit is 0, we raise that line. And if the bit is 1, we raise this line. We're actually sending 2 bits, which we encode as a 1 and 4. So we have 4 lines, and we raise one of them to encode all the possible combination of 2 bits. But that works just like this. And so what you can see here is we've got the source is going to actually send a request to the sink that says that it's got a packet that it wants to send. And then when it gets enabled, signal back from the source, from the sink saying that it's ready, then it's going to actually start sending data. Either raise this line to send a 0, raise that to send a 1. In both cases, it waits to get an acknowledge back from the sink, which does acknowledge by taking that enable line low, and then it resets its data line. And then we start the next cycle. And so we keep doing these 4-phase cycles to send each bit until the source is done with that whole packet. And so then at that point, it takes down this, what we call the phi, and says that's the end of the packet, and the enable also goes away. And generally, when we design these circuits, we work at a higher level of abstraction. This is the handshaking level. This is called the communicating hardware processes level, or CHP, where we just say, okay, this is the head of the packet, send the data, 0, 1, 0, and then this is the tail of the packet. So this is, communicated, represented by these 2-phase communications at the beginning and the end, head and tail. And then the others are communicated by these 4-phase. They expand into this 4-phase handshake. And this one expands into that 2-phase handshake. And even more abstract, you can just say, okay, X bang bang X, which means just send it serially on that channel. Okay. So that's basically how we follow this synthesis procedure, starting with this high-level description down to the actual logic circuitry. And that's available on GitHub. I'll give you the link at the end. And so once we laid out the whole thing and we instructed the layout, we run a SPICE simulation of what happens, how fast can we go. We took 2 leaves here, which are, daughters of the same node here, and they requested simultaneously. And we had to basically generate those 2 packets, and spit all those bits out the tree along this path. Sorry about that. So, okay, so what does that look like? Okay, so these are the results of the spice simulation. Let me walk you through this. So you can see here, two of the pixels actually requested simultaneously at this point. That would be like the request from the pixel. And then the parent of those leaps basically then took an active low file signal down to request that it wanted to send. That cascaded up the tree to the top. And then outside the array, the digital circuitry out there, enabled it to send, okay? So then it didn't send the data all the way from the top. First, it sent the bit or the 1 and 4 signals. It raised 1 of 4 signals, telling it which of its 4 daughters that data was coming from. So in this case, this green is like, line number 0, okay? And then having done that, the environment acknowledged the receipt of that signal by taking this low, and so then this communication ended, right? And then now this node here then started sending data from its daughter, right? Which told it that, well, this is where my data came from, so it also sent a 0 signal, and which propagated up the tree, and which was acknowledged, and then it kept going down and down and down and down, taking a little bit longer each time, such that the last time communicating the bit all the way from the leaf out to the top took about 4.3 nanoseconds instead of 1.3 just at going between the root and the environment. Okay, and then that basically was the end. Then this guy was acknowledged, and so this pixel withdrew its request, at which point its parent was able to then, actually it went ahead and requested again, but its parents ignored that and picked the other pixel that was waiting and did the same thing. And you can see these bits are different for that pixel. And then this was the end of the communication of that packet for that pixel, which also requested again, and we can start again here, okay? So we were very happy with these results, and we sent the chip out for fabrication and got a little surprise when we actually measured the cycle time here and got 18.1 million events per second instead of 42.5, which you expect from this 23.5 nanosecond cycle time. It turned out to be due to a rookie error here, where instead of putting a buffer here and handshaking right there, we had to send the signal all the way over to here and then get the acknowledge come all the way back. And so that slowed things down. But if you got rid of that, I'm pretty confident you get over 40 million events per second. And so to summarize, basically we proved the concept, and basically these races, match delays, and whiteouts were eliminated by taking this tree-based approach where we place the interface circuitry underneath the array instead of on the periphery, get rid of those whiteouts. And we actually implemented a fully delay-insensitive asynchronous version of this, and it worked robustly. And we expect to be able to achieve about a 23.5 nanoseconds cycle time if we get rid of that rookie mistake. And that's enough to support a 256 by 256 array at 650 events per second per pixel. But of course, we want to go bigger than that, right? Prophecy is at 1280 by 720. So can we do better? Yeah, there's lots of room to improve this design. This is really the first proof of concept. And so if we look at our results in the bit serial case, when we communicate bits serially, our cycle time goes like T0. This is the overhead for setting up the phi, the head and tail of the packet. And then depending on which level the bit is coming from, at the nearest the root of the tree, it takes just 1.3 nanoseconds. And then each additional level of the tree adds about 0.6 nanoseconds. So this is based on the simulation results shown here. And so if we were to pipeline it, in other words, put in a pipeline stage between each level of the tree, then we could actually not have to wait for this whole thing to propagate up. It would just be queued up across the different levels of the tree. And so then we could maintain this T1 cycle time across the whole thing, and that will reduce the whole transmission to 14.3 nanoseconds. And we could improve even further if we went parallel, where these bits were sent in parallel. So we just add more and more lines as we go up the tree, and we keep the buffering in the pipeline, but the bits just come out in parallel. And in that case, we expect to achieve something like 1.3 nanosecond cycle time you see here, and which is enough to support somewhere around 20 events per second per pixel. So that's getting up there with competitive with what is being achieved now. And so, yeah, so if you're interested in this approach, we'd love to hear from you. And we want to acknowledge ONR for funding the research, as well as Gray AI Model Labs, and Crystal Poch for providing the video that I showed of the prophecy camera. And for more info, you can read the paper, and you can also look at the circuit design stuff on GitHub for the logic. Okay, thank you very much.